Hello everyone, today we will see another example which we can solve easily using the Feynman's technique of integration. The question is to solve the definite integral from 0 to 1 log of x plus 1 over x square plus 1 dx. Now how to solve it? We first introduce a parameter. We take a function I of alpha as integral 0 to 1 log of alpha x plus 1 over x square plus 1. Here we have just introduced the parameter alpha. We define I of alpha with the help of the given integral only, making sure that if we put alpha equals to 1, we are going to get the original integral which we have to solve. And if we take alpha equals to 0, we get I of 0 as 0 because in numerator it will be log of 1 which is 0. Now the next step is to differentiate both sides with respect to alpha. So this is what we are going to get. Now using the Newton-Leibniz differential under the integral sign, we have to take the partial derivative with respect to alpha, which you can see here. The partial derivative we can get as 1 over x square plus 1 times x over alpha x plus 1 because x has been treated as constant here. Now, once we get this, what we can do is we are now left with this integral to solve. Now, how to solve this integral? So, to solve the integral, we'll first use the partial fraction method to decompose it. For that, we write it into the form ax plus b over the quadratic term, which is x square plus 1, plus c over the linear term, which is alpha x plus 1. Now, if we compare the numerator and we multiply everything on the right hand side, we are going to get this type of quadratic expression. If we compare the coefficient of x square and x, we can compute easily the value of the coefficients a, b and c. So if we compare the coefficient of x square, we get a times alpha plus c equals to 0. For coefficient of x, we get a plus b alpha equals to 1. For x raised to 0, we get b plus c equal to 0. From the third equation, we get c as minus b. And from the second equation, we get b as a times alpha. And simplifying the first expression, we get the value of a as 1 over alpha square plus 1. B value, which is a times alpha, so it will be alpha over 1 plus alpha square. And c value, which is minus a, so it will be minus alpha over 1 plus alpha square. So we got the value of the coefficient. Now we will just substitute the value of this coefficient into the original integral and we are going to get this type of expression. Now you can see here there are three integrals. So we will separately evaluate all the three integrals. So if we evaluate the first integral, which was x over x square plus 1 dx. So the derivative of denominator is in the numerator. Just we have to multiply and divide by 2. So we get that integral as half of log x square plus 1. Putting the limit, that is log of half of log of 2. Second integral is given as integral 0 to 1, 1 over x square plus 1. That is nothing but tan inverse of x. Putting the limit 0 to 1, we get tan inverse 1, which is pi over 4. For the third integral, which is given as integral from 0 to 1, 1 over alpha x plus 1. So that is basically log of alpha x plus 1 over alpha. Limit is 0 to 1. So if we substitute x equal to 1, we get log of alpha plus 1 over alpha. Now if we put all the value of the integral into the given expression which we got earlier, this is what we are going to get as our di over d alpha. Now what we have to do, we have to just integrate these both the side with respect to alpha. So what we are going to get? So I of a will be log of 2 tan inverse of a plus pi over 8 log of 1 plus a square minus I of a, which we have to find out. So if we take a equals to 1, this is what we are going to get. 2 times I of 1 will be equals to pi times log of 2 by 8 plus log of 2 by 8. That is pi times log of 2 over 4. So I of 1 will be equals to pi times log of 2 over 8. So this is how we can easily solve the integral using Feynman's technique of integration.